Bene, buongiorno a tutti. Yesterday we started with the formal analysis of dielectric waveguide. That is a structure that is able to confine and propagate the light along the direction. Dielectric waveguide works at every frequency. I mean, you can use those in the microwave regime or radio frequency regime, but are particularly useful at very high frequency, so for the light, to propagate the light. However, we discussed about waves and never we say light. So you can think the electric waveguide also in the microwave regime. In the 40s, probably 1940, there was some example of light propagation, a microwave propagation, radio frequency propagation in dielectric rod, cylinder of dielectric material, especially to make antennas or to make other high frequency for that time, few gigahertz frequencies. So we used an approach yesterday, so-called ray optics. Ray because there is this sort of beam that bounces up and down in the waveguide, so I probably have to wait a little bit. No. So this so-called ray optics approach is quite easy to understand, intuitive, of a wave that undergoes a total internal reflection at the interface between two dielectrics, and so goes in this direction, up and down. The picture is, say, intuitive, but it's not very realistic. we achieve a number of results, in particular the existence of modes of the waveguide, the characteristic equation of dispersion equation, and this permitted to achieve and calculate the phase propagation constant of the wave. And what else? Well, nothing else. So it's a good start, very fast results, but then we cannot continue. So at this point, it's better to stop here and continue with an electromagnetic approach. So with a wave equation, Maxwell equation, wave equation that I told you yesterday. Yesterday, I explained you the path, how to do it. So this morning we use this approach, wave equation, try to solve the wave equation analytically, and so calculate once again the characteristic equation and the modes and the shape of the modes and everything else, all the characteristics of the waveguide. It's not easy to do, so we choose the simpler structure as possible. That is a slab waveguide. Slab. So let me use the same symbol of your NW, the refractive index of this plane, infinite plane. We call it zeta this direction, and x this direction, perpendicular to the slab, and the y is in the direction perpendicular to the board, but is really it's not meaningful because it's absolutely uniform, the waveguide in this direction. So it is infinite. We call it NC the cover and S the substrate, the refractive index of this wave. So it's a sort of slab, planar slab, like this table of dielectric, infinite in this direction. So so it's a 1D problem. Because it's just one direction, is x. Zeta is the direction of propagation, but we know that the dependence on zeta is of this kind, plus minus beta zeta. So this is the assumption. So the problem is easier. And let's try to solve the propagation of this. So you have to take the Maxwell equation, and when you take the Maxwell equation in 1D, for this case, you immediately realize that there are two solutions. One for which the magnetic field in the y direction, so in this direction, is equal to the electric field in the vertical direction, and is equal to the zeta component of the electric field that is 0. So one of the solutions has these properties. And this is called the TE solution, transverse electric mode. There is another solution with EY, HX, HZ equal to 0 that is called the TM mode. So you realize immediately from the beginning that there are two solutions. One is called transverse electric, the other one is called transverse magnetic. So these are the two family of modes that we found today, and we will bring it till the end of the course. We mainly focus on the TE, because it's usually the most used, is is simpler to use, and we consider that solution, even if the TM very often, and especially in low index contrast waveguide, is obviously used. So let's consider the T. The TM is very similar. You have to change the electrical magnetic field. So the other Maxwell equation gives you a relation between the X component of the magnetic field and some other component of the electric field. Remember that we consider the frequency dependence sinusoidal as usual, like this, and we never write this term because it's supposed to be everywhere. So these are basically the Maxwell equation, and you can combine to get the wave equation for this lab waveguide. K is 2 pi divided by lambda, is the wave vector in in a free space. N is the refractive index of the material. So if you are considering this equation in this part, in the core, N is NW, N of the waveguide. If you consider this equation here, is N of the cover. If you consider here, is another refractive. So it depends on the position, right? Okay, so now we have to wait. This is much simpler than the one that we wrote yesterday. Is a scalar. The electric field, you see, we have only the component EY. So it's not a vector, but it's a scalar, much simpler. And it's a second order equation. So you can try to solve this equation. We are not really interested in all the possible mathematical solution, but we are interested in the mathematical solution that has a physical meaning. And the physical meaning, important for us, are the modes that can propagate. So we are looking to this part of solution. Okay, so how to do it? The most simplest part is to assume a solution in the three homogeneous region, and then impose the continuity of the field at the two interface, as we explained yesterday. You remember, if you look at your note yesterday, we said we use a variable separation technique, and we write the generic solution here, here, and here, and then we force the continuity of the field at the two interface. So we have to do exactly the same. So we have to write, so let's assume that the origin is here on this interface. So assume that the height of the thickness of the slab is h. So we have, for this part, is where we assume all the light is concentrated. Let me write here. So for x in between 0 and h, so in this part, we assume a solution, some amplitude, given amplitude, and then what? Well, is a rectangular coordinate system, a Cartesian coordinate system, so we have to use trigonometric function as basis, so cosine or sin. So let's write the generic solution. The cosine of, well, x through some coefficient, so we write k of the waveguide multiplied by x And then we have to add the sin part to be complete. Sin and cosine is a complete basis for the field. Or we can combine the two and add just a phase term. So you can write the generic solution as a combination of cosine and sin, or just a cosine with an offset. And this is a complete solution. You can describe every field in this way. These are just coefficients that make sense from a mathematical point of view, because it permits to scale the cosine, offset the function, etc. But when we finish, we will see that there is a very clear physical meaning. Okay, right. So we have the field here. And then above, so for x larger than h, so the cover part. Once again, we are in a Cartesian coordinate, so is once again sin and cosine. However, probably, and we say that the light is confined in this part of the structure. So we have to assume that the field is here. Obviously, there is a field here, because yesterday we saw when you have total internal reflection that there is some field in this part, but for sure not at the infinite. So cosine and sin does not really represent the good way to represent the field. So you can use another basis, that is the exponential. So we assume that the field in that part is once again a coefficient, amplitude coefficient, and an exponential part that describes the field there. I should use as a complete basis also the terms plus gamma. But this has a physical meaning of a field that increases going away from the waveguide. And it's not really realistic to think to a field that becomes larger and larger as you go away from the waveguide. So mathematically, I should have included also this term, because this and this is again a complete basis for the description of the problem, but this does not have a physical meaning, so I do not include in the. And the same for the substrate part. So for x minus lower than 0, we have once again an exponential decay. So is a gamma x plus, because x is negative and does not has any physical meaning, include the exponential with a negative sign, and is just a gamma because we took the coordinate on this surface, so is h, is x. Okay. If the refractive index of the cover is different from the refractive index of the substrate, these two gamma are different. So we have a gamma of the cover and a gamma of the substrate.
The substrate is growing and the upper is
no, because x is negative here, and so I have to include the. So let's remove this part that has no physical meaning. Okay. Any question till now?
So I didn't get well, that part was mathematical, yes, but you will cancel now. Why was the reason of the mathematical including of the exponential with the exponent?
In a Cartesian coordinate, rectangular coordinate, the basis function is cosine and sine. With a combination of these two, you can describe every function. Fourier. If you think to a cosine of an imaginary part, you can write this one as e to j, so jx cosine jx divided by 2, right? And the same sine. So I can use as basic cosine and sine or the two exponential. And you can have a real or imaginary exponential. So this is the, I could write here, for example, the sine and cosine with the imaginary argument. But this is a more physical, immediate physical meaning, so it's easier.
In the beginning, in the WaveGuide, the expression was a cosine. Can you explain one more time?
Every kind of, I don't know the shape of the field here, but every kind of field can be described with a combination of cosine and sine, for sure. So I can write a combination of cosine and sine or a cosine shifted with respect to the origin. It's the same. So the second step is impose the continuity of the field at the two interface. So you have to put this solution inside the wave equation. So for example, for the upper interface, this one, you have to put EY with x equal to h, so this becomes 1 into this equation, and the same this one into this equation with x equal to h, and impose the continuity of the, for example, the tangential EY field. So what you get is this relation, very simple, kw to the square equal to k to the square and w to the square minus beta. And if you do the same on the other discontinuity, you get something like this. And if you can, if you like, you can rearrange this in order to get another one, that is this one. So from a mathematical point of view, this is just a relation between the various coefficients that we put in the solution, that we assume, that we imagine. So these are not totally free, all these coefficients that we put inside, but a relation between them exists because of the continuity of the field and interface. This is a very important physical interpretation, but in a couple of minutes, before we can try to combine this and get an expression, rather complicated, but this is quite interesting. We combine this and we get this relation . So we find a relation between the various coefficients. We basically eliminated beta, the propagation constant, from this set of equations. The detail how to arrive here are written in the notes. It's not very important. But what is important is that we arrive to an equation that we call it characteristic equation. So this tells you the relation between the various parameters, so give you the solution of the problem. And it's possible to demonstrate that it is exactly the same of the characteristic equation that we found yesterday using the ray optic approach. Let's see what is the physical meaning of the various coefficients. We assumed the field outside of the core, so in the cladding, the cover, or in the substrate, as an exponential decay. So gamma, that we find here, is just how fast the field decrease going away from the waveguide. So the field, whatever it is the value here, the interface, decrease with the speed, with the velocity, E minus gamma cover x. This is E gamma substrate x, apart some coefficient and shift. So it's an exponential decay outside. And this comes because of the rectangular system of coordinate and geometry. If it is not rectangular, as in optical fiber, it's not exponential. And here, well, here we have a cosine. The shape of the cosine depends once again on the relation between gamma c, gamma s, the refractive index, etc. But it will be something like this. Must be continuous. So this is continuous. Yeah. This is the lowest possible value of Kw. But you can imagine also solution with a higher value. So you can imagine solution, for example, like this. Continuous here, but if you imagine a larger value of coefficient of argument of the cosine oscillates faster, so you can have shape like this. So these are the modes. So with this approach, we are able to describe the shape of the mode. Yesterday, we understood that outside of the of the waveguide, the behavior was exponential. You remember, I wrote the wave, the plane wave in this part, etc. But we had no information of the side. So this is something more, and we are able really to find the shape because these coefficients now are known. Not very easy to calculate. We don't have an explicit relation. We cannot write gamma c equal to blah 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 because it's complex, because there is a trigonometric function, etc. But numerically, it's quite easy to do. Okay. So, from a mathematical point of view, now I guess that more or less you understood how to proceed. Huh? And now I want to give you the interpretation of the various coefficients that we put inside the. We already understood that the physical meaning of these two is the shape of the mode, give you the shape of the mode, but there is something more. Let's this one. This one, okay. If you look at this relation, you probably remember the Pythagoras theorem, no? So you can imagine. Let me write here these two lines, if you understand clearly what it is, and let's consider the first one is something like this. This is a triangle with beta, NWK, and KW. KW to the square plus beta to the square is equal to this term. So this is just the Pythagoras theorem of the first relation. Okay, which is the physical meaning of this? So beta is the phase propagation constant of the mode. The refractive index of the core multiplied by the wave vector of the free space is the wave vector of this material. 2 pi divided by lambda NW is the wave vector of that material. And KW is the transverse wave vector. The name is transverse wave vector. And to conserve the momentum of the sum of the three vector sum of the three must be of these two must be equal to this one. So you always have for a wave in a given structure in a given material a relation between the wave vector. So this is the wave vector of the mode that we call it the propagation constant or phase constant, the transverse transverse wave vector, and the material wave vector. And the same is valid for the other two regions. In the other two regions, we have something similar, but you see that there is a different sign. So the triangle is a little bit different. We have beta that is beta, exactly the same, so same dimension. Gamma S and K N substrate. Okay? Everything is written in your notes, so don't copy them. No. So, in this part of the space, we have a wave that propagates in the zeta direction with this phase constant, beta. It's not possible, another one, because this part of the field and this part of the field are a part of the mode. They may have to move in the same way. So we cannot have two different beta because of the continuity of the field here at the interface at every point. So the only way to have the continuity all over the propagation direction is to have the two beta identical. So beta and beta. And this is given by the solution, by this one. Then this one is the wave vector of the material. So it's this one. We can do nothing. This is the material of the substrate, and this is 2 pi divided by lambda. So the only part that can be adjusted in order to close the triangle is this one. But in this part, beta is larger than the wave vector in the material. So gamma, or the wave vector is imaginary. So for this reason that we use the exponential, we don't use the cosine, and the triangle is like this. So this field has an exponential decay, gamma, propagate in this direction as his friend in the core, and it does not propagate along x, because along x the dependence is this one. There is no J here, so there is no propagation away. If there is no propagation in a direction perpendicular to the waveguide, it means that the energy is confined around the core. Does not lose energy, energy does not go away, and continue to be localized around the core along the propagation, along zeta, along the waveguide. The shape remains the same. Is a mode. All the characteristics of the mode that we have discussed yesterday. I can do the same for the upper part. So we have a beta here, exactly identical to the other one because of the continuity of the field, the gamma, and the wave vector of the cover material. And this is gamma. This is beta. So we started to solve a differential equation. We tried to do it mathematically. We put some coefficient, and we found that this coefficient has a physical meaning. The physical meaning are the shape of the mode, so the distribution of the electromagnetic field around the core, and the wave vector in the various parts. And this is true for every structure that guide something, that guide an electromagnetic wave, that guide the light, that guide the vibration, that guide the heat, that guide the fluid, and so on. Every time you have a wave equation, and you have many wave equations, you get something like this. So the string of a guitar, a pipe that brings the water around, the electromagnetic WaveGuide, cable, or what else? Hmm? We say yes, we can have a higher value of this coefficient. What does it mean? That we have more oscillation of this. This is 3, we can think to 5, etc. But what does it mean here? That you are increasing kW. So if kW becomes too large, this is fixed because it depends on the frequency and on the material of the waveguide. And you always must close the triangle. So if this one minus this one is negative, beta is no more real, becoming imaginary, so the solution does not exist anymore. Yesterday we said that the number of modes is discrete and there is a limit. It can be 1, 2, 3, 100, but not infinite. And this is reached when beta becomes imaginary. At that point, your wave becomes something like, I don't know how to call it, let's say once again beta, or modulus of beta, zeta, and this is not more a wave that propagates. It's just a field that attenuates, that evanescent decrease along the propagation. This is above the cutoff, once again. Does not propagate anymore.
When kW increase, how turn it to be when kW increase, how turn it to be immeasurable?
When kW when this one increases, when this one increases, well, it if this one increases, at some point beta become negative. And this is the square of beta that becomes negative. So beta becomes imaginary. Like this. Obviously, if I increase this one, at some point this one becomes negative. So if I write this is the axis of beta, which is the minimum value of beta, which is the maximum value of beta. What does it mean, beta larger, smaller, of this range or inside this range? Here we have n cover wave vector of the cover. We have k and s, so the wave vector of the substrate, and here we have k and w, so the wave vector in the core. Spark. look at this part. So beta can range from this point to this point. So here we have the solution, the guided solution. So these are the guided modes when beta is included in this range. When kW become equal to 0, you are here, and when sorry, here I make a mistake. This is gamma c. When you have a gamma equal to 0, we have this value, and when you have gamma c equal to 0, we have this other value. So these are the guided modes. These are called the radiative mode. This is 0. Why radiative mode? Why radiative mode? If we have a value of beta that is lower than K and S, it means that this difference is negative. Is positive. So gamma square is negative. So the square root of a negative number is imaginary. So our exponential field become propagating field in the x direction. So the mode started to propagate in this direction. Yes, sure. Assume that you calculate, you find the solution of this equation, no? And you find the value of beta, of the coefficient of beta, that is smaller than this value. Okay? So if you look at this relation, it means that this difference is positive. This one is smaller than this one, so this is negative. So gamma s is is imaginary. So it means that the behavior of the field in the substrate of the cover, now that what we talked about, say, one of the two, is no more exponential decay without propagation, like going away from the waveguide, so in the x direction, but is a wave. So we are losing energy. So the mode is losing energy. So this is called the radiative mode, and is the continuous part of the spectrum that I wrote yesterday. Yesterday I wrote the solution can be, it was written here, a combination of mode plus a continuous. These are the radiation mode. Is this part. So this part is the mode, guided mode, discrete, and this part is the radiative mode. That is a continuous because beta can assume every value in this range. But this is no more a guided mode because it loses energy propagating in the waveguide because it tends to abandon the waveguide, irradiate away. So you're losing energy, power goes away, and if you travel along the waveguide, at some point there is no more light. So a radiative mode at the end is a plane wave. That is a mode of the free space. there is a point when beta look at this relation, for example. When gamma s is equal to 0, we have 0 equal to nsk to the square minus beta squared. So when beta is equal to nsk, this is the transition point. The field is no more decay, exponential decay, but is a wave that starts to propagate. Exactly at the point, you have a 0. So how do you call this condition? This is a cutoff. Difficult to understand what happened at the cutoff exactly, but a little bit before the mode is guided, a little bit after the mode is no more guided and radiate away. So that is the condition of cutoff and correspond to the critical angle of the ray optics picture that we discussed yesterday. Sorry for insisting a little bit on the waveguide, on the propagation, but I would like that you have clear in mind what happens. Make your movie, make your imagination what's happened to the field in the waveguide, how it's confined, how it's stopped, how it's propagated. No? Try to make your own interpretation, the correct one, hopefully, and keep them for the entire part of the course. So, this is the cutoff, and if you play with this one, you get the expression of the cutoff wavelength, and here we have closed form formula relation that give you the cutoff. The one for the symmetric slab I gave you yesterday, you remember. Maybe you want to write it again. Let me say if it's around okay. This is for a symmetric slab is 2 divided by, yesterday we used n, I think. Yes, n, thickness of the slab, square root of nw to the square minus n substrate to the square. If you play with this and this, you get this solution. It's not really okay, it's interesting to also to ask what's happening in this side. We from 0 to this point we have radiative mode for the cover. From here to here, radiative mode, well, cover and substrate. From here to here, radiative mode of the substrate. Here, guided modes. So beta can assume all this value and then some here because it's discrete. And on the other side, on this part, do we have solution there? We do not have a solution there. Why? just take the wave equation. If we have beta in this region, this part, here, it means that beta is larger than every one of these value. So it means that this part is positive in the free region. Here, here, and here. It's always positive. But this is the second derivative. So this means that it's a paraboloid, no? It gives you the curvature of the field. So if the second derivative is positive, it means that also this one is positive. So it means that the solution is no more something like this, but is, let me draw here. So inside the core is a cosine C. So once again is something like this. And then outside is something like this. So we have, you see, the second derivative is also always positive in every point. So the value of beta in this part means a field that continue to increase as you go away from the waveguide. Does it make sense physically? Mathematically, yes. So we have solution here. But physically, no. It's not possible to have this solution. So this is a forbidden region, physically forbidden. And there are no solution there. There is not possible to excite the mode, put the power, or put a shape of the field with the beta in this part. All this story is valid for a wave that propagates in the positive direction of zeta. But obviously there are also the solutions that propagate in the negative direction of zeta. So exactly this should be drawn also on this side. So let me cancel all this. And so we have here minus K and C minus K and S minus K and W. And once again, we have a radiative mode till here and guided mode here. And these are waves that go back in the opposite direction. Okay? Now, the solution, so the value of beta, depends on the geometry and the physical characteristic of the structure, so the refractive index and the thickness of the slab, and also on the frequency. So if you put on this axis the frequency, unfortunately I draw this on top. I should have done it here. Let me shrink the plot and then I show you the right picture. So if you put on this axis the frequency and you place solution at the corresponding frequency, you get the so-called omega beta diagram that I showed you yesterday. Sorry for the terrible doing. Now I show you the good. But basically the story is this. So at this frequency, we get this solution. While at this frequency, we don't have a guided mode. And we never arrive to this part. There are no solutions. Okay. Questions on this part? A lot of concepts this morning. Tired? A little bit. Questions?
Just curiosity, if we increase the frequency because we want to transmit with high frequency, there is a point in which we can not propagate with one single mode if the medium is not appropriate, because if the curve is like that and there is like an upper limit to propagate with a high frequency, we have to have a better material. There is no.
Trying to understand your question.
Okay.
First of all, you say that we want to transmit with high frequency.
It's not. So, there was the.
No, just to be sure. There is the carrier, so the light, and then the signal. So when you want to transmit at high frequency, what do you mean? As carrier or as bit rate?
As carrier with high frequency to have a better penetration. Or
Well, as carrier, you use the best frequency.
okay, so
For an optical fiber in glass, the best is around 1.5 micron. So you say stay there. You don't want to use the visible light or UV or X-ray, no?
But for example, we have that lambda is 1.5 micron.
Yeah.
But to have that frequency, okay, with lambda at 1.5, we need to have a material that with kappa n, right? Because
with NW.
yes, not because the curve is like.
Well, first of all, you need a transparent material. That is the most important, right? And then you need a structure with the refractive index of the core higher than the refractive index of the cladding. This is the condition.
Yeah.
To have this picture.
Okay. Yes, but it was only on the how the curve is made, because it's like a sinusoid, like.
No, it's not a sinusoid. Let me show you the well done. this is a European project, it's not the correct one. Here. Okay. Okay, this one makes sense. So this is the omega beta diagram. If you do another say, is lucky or not. So this is the beta axis, only positive. This is omega, and this line, this one, and this one, and this one have a slope of c, speed of light, divided by the refractive index of the material. So this is the speed of light divided by the refractive index of the cover, of the substrate, and the waveguide. So your solution stay along this line. Okay.
But if we have, if you want to, for example, have omega that is very high, so up.
Like this?
Yes, for example,
Okay.
we have we need a material which, for example, W is yes there. Yes. If you want to work there with the frequency, to have a single mode propagation, we need a particular material, no? It's not
No, for a given combination of material, cover, substrate, and waveguide, and for a given thickness of the slab, you have these kind of solutions. So if you work at here at this frequency, the structure, not the material, the structure, so the thickness, the combination of refractive index, give you two solutions, 1 and 2. Okay, so there are two modes, two configuration of field that satisfy all the conditions that we have said and that can propagate along the waveguide.
and then I choose between one or the other if you want single propagation.
Okay, thank you for
That
pointing
was
out
the
this. This is very important point. So these are the solutions. Think to a highway, a highway with, for example, 2 or 3 lanes. These are the mode. The lane are the mode, and these are the solution. So you have 3 lanes. Then you can occupy the 3 lane, only 1, only 2. Okay. So this is how you put the information on the mode. So if you have a road with just 1 lane, this is a single mode road, and with your car you can stay only on that lane, single mode. But these are two different concepts. One is the solution, the mode, the lane of your road, and this is a property of the waveguide. It's a property of the road. And the other one is where you put the information, the energy, the light. So if you have just one, you have no choice. If you have 2, you can choose. Okay? So you can use a highway with a 5 lane as a single mode. You keep your car exactly in the same position. But you can excite also the second mode, the third mode. So choose the lane. if everything is straight, you stay on a, and if you don't get asleep and move away, you keep the lane and you stay on the lane. But in a bend, for example, it's easy to move, to shift to other modes. So there are two different concepts. One is the number of solutions available, and the other one is the use of the solution. So this is a much better picture than the one I showed you before. And so we have this region. In this region, we have the guided wave, guided solution, the guided mode. This is the forbidden region. You never can reach this part. And this is the radiative mode part. And this is the cutoff. If you reduce, if you stay here at frequency, you have two guided modes, 1 and 2. If you move down, at some point you arrive here, you have one guided mode, and this one is at the cutoff. So if you increase a little bit, it's guided. If you decrease a little bit, it's no more guided. If you decrease even more, you arrive here. Here you have one mode. Here is the cutoff of the first mode. And if you decrease even more the frequency, at that point there are no more solutions, but only radiative solutions. You are not able to propagate any light along the waveguide. Okay? And below, you see the triangle that we considered before, the picture. So in, for example, 3, here, these are guided mode. You see that here you have a guided mode in the core with evanescent behavior outside. In this case, we have 2, a guided wave in the cover. So here you have a total internal reflection, while here is no more guided. So you don't have total internal reflection here, and you lose energy in the substrate. So this is a radiative mode of substrate. And after this point, so here you have radiative mode both on the substrate and on the cover.
Radiative mode is exponentially increasing, or it is
So the
radiative mode. It takes from the power of the waveguide. However, it is exponentially increasing. How speed looks like
not easy to say. Now I show you. We go a little bit better in this direction. Formally, radiative mode is a plane wave. It's something that is no more guided by the waveguide. So it's a mode of the continuous. Is this part, radiative modes are plane wave. This wave is a solution of the free space, and so is really plane wave. So how it looks like is, as you know, a plane wave is a mathematical object, does not exist in practice, because a plane wave is something that has been generated from a source that is in the infinite, no, because now it's plane and is infinitely large, so does not exist a plane wave. The light of the sun is a plane wave, to be correct. But sometimes it's a good approximation of the reality. Okay, and what else? So now we have to talk about the shape of the mode, look a little bit better about the shape of the mode. I want to say something for beta, on beta, and I want to introduce the leaky mode. So, let's start from the shape of the modes. In a slab waveguide, we have seen that we have for a guided mode a cosinusoidal shape in the core and an exponential decay of outside. So this is our slab waveguide, and the shape of the mode is more or less this bell shape, Gaussian shape, or whatever, not clearly Gaussian because it's exponential. No? If you change the frequency or the wavelength, the shape of the mode changes a little bit. This is the fundamental mode. And if you increase the frequency, reduce the wavelength, the light is more confined in the core and there is less field outside.
By increasing the
Frequency, yes. These are other solutions. This is the fundamental mode, so just a cosine here and two exponential outside. But if you increase the transverse wave vector, you have more oscillation inside the core, so you get a shape like this, second mode, or like this, third mode. Outside is always exponential. These are asymmetric waveguides, so you see that the behavior outside is different, is not symmetrical, because the waveguide is asymmetrical. And you have a number of oscillation here that depends on the KW, so the transverse wavelet. Look at this behavior. Here, the exponential decay is very fast. No? Very rapidly goes to zero exponentially and then is very small. Here, decrease exponentially but very slowly. So here we are moving toward the cutoff. At the cutoff condition, gamma is equal to zero. So you have here something like this. This is another picture to show you in a little bit picturesque way the three class of mode that we have considered before. This is a guided mode. Cosinusoidal shape, exponential, exponential. This is a radiative mode. Here is a cosine function because the solution considered is a cosine. Here is guided, so we have an exponential decay, but here is no more guided, so we have a light that propagates down and go away from the core of the waveguide. And this one is once again radiative, but both substrate and cover. So these two are not modes. It's just something that is riding a wave, is losing energy. So this is a guided mode.
Even the last two ones, the substrate mode and the disperse substrate mode, there is no guide in the mechanism. There is no guide.
Okay, now I'm coming to the leaky mode concept. I want just to touch, quite difficult to represent mathematically, but just you have to make the effort to visualize. From a mathematical point of view, we have guided mode, a radiative mode. A radiative mode are plane wave. However, when you arrive close to the cutoff, no, as in the previous one, okay, assume to decrease a little bit the frequency of this mode. No, what happens? Well, this part goes up, and at some point you start to lose power from the core, and there is energy that go away. You see that inside the core, the shape is recall you something, recall you a mode. So this is no more. This is no more a guided mode, but the shape is similar to a mode. This one is not able to propagate for a long distance, but it is able to propagate a little bit before lose completely the energy. So it's a sort of intermediate condition. It's not guided, but it's not completely radiative. It makes some distance before going away. These modes are so important, let's say, or can have an effect that people give a name to this mode. And these are called leaky mode. So is not a guided mode, but we can call it mode that lose energy, so leaky. So we call it leaky mode.
You mentioned you said about radiative mode, quiet mode, and right now I see the substrate and superstrate. What can you do with this?
If you like the ray optics propagation, the ray optics explanation of yesterday, the guided mode is something that you have a total internal reflection at every point. The substrate radiative mode is something that you have total internal reflection here, but not at this point. So you lose the total internal reflection condition only on the substrate. And then if you decrease even more the frequency, at that point you start to lose also the upper part. If the waveguide is asymmetric and if the... So, a leaky mode, we can see the leaky mode as a combination of a radiative mode, the combination of plane wave that at some point of the space, for example here, has a well-defined shape. And then when it propagates, it goes away. But assume to be just a little bit before the cutoff, few hertz before the cutoff. Mathematically, it's not guided, the mode. The mode cannot travel for kilometers, no? But it's not guided, it loses energy. So, for example, in integrated optics, where all the components are close to each other, maybe the mode is not guided, but arrive to the next device, the next discontinuity, the next, no? I don't want to go too much into detail, just to let you know that exists also this strange condition that cannot be considered totally radiative, but is a badly guided mode. Let's call it like this. These are the names, leaky mode. I have 5 minutes, so I can to try to conclude on, on this part. We mentioned we talk about beta, and beta is the phase constant, so 2 pi divided by lambda multiplied by this effective index that is a mix between the core and the substrate and cover refractive index. So it's an average refractive index seen by the mode propagate. Okay? The phase velocity is defined as omega over beta. And if you substitute, you have 2 pi multiplied by the frequency. The frequency is c divided by lambda divided by beta, 2 pi divided by lambda, effective index. So the speed velocity is, phase velocity is c divided by the effective index. But there is another speed that is very important. It is the group speed, the group velocity. The group velocity is defined as the derivative of omega with respect to beta. And we can define this velocity as the speed of the light divided by the group index. And if you do some calculation, well, it's better to write the group velocity as 1 over the derivative of beta with respect to omega. You have the expression of beta, so you can derive beta with respect to omega. The effective index depends on the frequency, because the material depends on the frequency, because the solution depends on the frequency. So what you get is that the group index, assume this expression, is the effective index multiplied plus omega and the derivative of the effective index over. Probably you have already found this expression in some other courses, and or you can define with the derivative with respect to lambda, so it's net minus lambda, and the derivative of net with respect to lambda. This is the same, exactly the same. You can derive with respect to lambda with the right. The group velocity is extremely important. We will use the group index we will see in many devices. And what is the group velocity? There is a very interesting book by Brillouen, 1960. And I think that the chapter is in my website, so you can download it. Read just the first few pages. This is interesting. 1960, he collected a number of contributions from very big scientists on the velocity. What is the velocity? It's not so simple to define the velocity. What does it mean, the velocity of a wave? And we are not talking, no, the 17th century or 18th, 1960. So not much time ago. And so there is the phase velocity, there is the group velocities, there is the velocity of the energy, the velocity of the front of the pulse, of the trailing edge of the, or the leading edge of the pulse. So everyone tried to give an explanation of what is the energy. So what came out, what is interesting for us is the phase velocity, and this is the velocity, the speed of the phase front of a wave. While the group velocity is the velocity of a group of frequency. So the velocity of the energy, or the velocity of the information, very often people say. So the phase moves, the phase move at the speed c divided by n, while the energy or the information move at the speed of light divided by ng. I should have. And this is an animation of what is the phase velocity and the group velocity. So this is a pulse. Let me. Salute. Okay, this is a pulse that propagates along a structure which effective refractive index depends on the frequency. If the refractive index depends on the frequency, this term is different from zero. The free space, the air, the refractive index does not depend on frequency, so the effective index and the group index are equal. But in our case, the effective index depends on frequency. So this term is different from zero, so the group index is different from the effective index. So here you see in green the carrier, so the phase, and you see that it moves at a different speed with respect to the envelope that is in pink, in magenta. So the two speeds are different, and usually the group speed, so the speed of the energy, is always lower than the phase velocity. I stop this one before you get seasickness, and this is true until you don't have a very strong variation of amplitude or variation of the refractive index in the bandwidth of the pulse. Otherwise, the group index loses the meaning of speed of energy. So there is the speed of the phase, and this can be even larger than the speed of light, because it's not a transmission of energy, so does not violate what Einstein said years ago. There is the group velocity. The definition is this one. It's so interesting because the group velocity is the speed of the energy, or the speed of information. And this is true only if you don't have a strong variation of amplitude and refractive index in the bandwidth of the signal. Okay.
The green is phase velocity.
The green is the speed of the green part is the phase velocity, and the green part is the carrier, so the phase. Yes. It does not bring any information, the phase. It's the envelope that brings the information.
The envelope represents the group velocity.
The envelope moves at the group velocity. Okay, we continue tomorrow on this topic with WaveGuide and bent WaveGuide. If you have any question, I'm here.